Okay, welcome to the next lecture, numerical analysis of ordinary differential equations. So we were this week starting with finite element methods for boundary value problems, and I've considered this special boundary value problem given here. So this linear boundary value problem minus ku primed all primed equals f on the interval 0, 1 with homogeneous Dirichlet conditions u of naught and u of 1 is naught. So this is the so-called divergence form of the second order problem that we've been studying in this section 6. As a first step to do the finite element method, we had to rewrite this problem in weak form. So in particular, we're going to formulate this problem in a much weaker space, namely the solution we're looking for is only needed to be continuous and have bounded piecewise continuous derivatives. And this can be done by multiplying the differential equation with a test function, integrating over 0, 1, and then using integration by parts. So we got the weak form, which is given here, and with the particular bilinear form AUV and LV given here, and proved existence and uniqueness of solutions of such a problem. And as we said in the proof, in the case where the data k and f is sufficiently regular, as assumed at the beginning of the chapter, then the two solutions coincide because we have uniqueness, and and we know already that in the case where k and f are sufficiently smooth, the above problem has a solution. It has to also be the solution of the weak form. Now, to approximate and to construct finite element methods, we now don't use the approach as infinite differences to just satisfy our problem on a finite set of points. Instead, we choose a finite set of test functions. So here we have an infinite set of test functions, any function in the space capital V. We now choose a finite dimension subspace VH of V, spanned, for example, by this basis, phi 1 to phi n, and we only satisfy our problem on this for all functions out of this subspace. So clearly, we have fewer conditions, and therefore we don't have the same solution. We have an approximation. But the finer this space gets, so the higher dimension this space gets, the more we hope it approximates the problem. Now, because we're finite dimensional, we have a basis, we can rewrite the whole thing as a linear equation system, AY equals B, and here is the matrix entries, and the right-hand side entries. And again, we can show existence and uniqueness. And one particular choice of such a finite dimensional subspace are piecewise linears. So this is this space where we choose a mesh in the same way we did for finite differences, but now we're not satisfying the equation at the grid points. Instead, we're assuming that we're testing our variational form, our weak form, only for piecewise linear functions, functions that are linear on each subinterval. That again leads to a set of basis functions, which are the so-called hat functions, and we can explicitly work out the matrix A above, which is now a tridiagonal matrix. And that's how I finished last time. Okay, now I want to analyze the error in approximating U with UH. And to do so, we first need a bit of functional analysis, but very, very mild. We're going to look at a vector space. So this space V and the space VH are real vector spaces of functions over the interval 0, 1. And a function, namely the bilinear form A, that I have defined above for the weak form is now a mapping defined on V cross V into R. So we take two elements of our vector space and we do some bilinear combination of the two elements and get a value in R. In this case, our particular example was a u v equals integral 0, 1 k u primed v primed dx. So we take a function u and v that has piecewise bounded, piecewise linear, piecewise continuous derivatives, so we can evaluate all these integrands and integrate them from 0 to 1. So this is now an element in R, what comes out of here. And so we've mapped two functions from V into R. The bilinear form is called an inner product on V if in addition it is symmetric. Now this example here is of course symmetric, and so it is also an inner product. Well, there's two conditions. So first of all, it has to be symmetric. If I exchange V and W, I get the same result. So here, if I exchange V and W, obviously I get the same result. It's linear. And if the second condition is that if I stick in 2 times the same argument, so if I stick in V primed twice, that then the result is greater or equal to 0 for all V and V, and 0 only for the function 0. And this we have already checked in the proof of existence and uniqueness. In the proof of existence and uniqueness. So that was lemma 6.4.2. So look back, we've checked already that for the specific bilinear form given here, this second condition holds as well. So in our case, we have in fact an inner product. If A is an inner product, this is again something you've already heard me. I have defined this before as well. We can define the induced norm. The so-called energy norm. So we denote it by subscript A for the bilinear form, and it's essentially just defined as AVV square root of AVV. And this satisfies, of course, Cauchy-Schwarz, which we'll need. It is a norm. So in particular, it satisfies Cauchy-Schwarz. So A VW in modulus is less than or equal to V in the A norm times W in the A norm. For all VW in V, and this will be our 641. Now let's consider our problem, but in a sort of abstract way. Now consider not specific with the bilinear form here, so not specific with this bilinear form here, but just abstract. So we want to find U in the subspace V, in the space V, such that A UV equals LV for all V in V. But we're not specifying that what A and L are, apart from that A is an inner product. And in addition, we also consider again the approximation 633 of finding UH in some subspace VH of V such that AUH VH equals LVH. Let me just make this clear again. By abstract, we mean that A and L are not necessarily defined by. We will apply it to that example, but they're not necessarily defined by 630. Okay, so now we have the following theorem. Assume A is a bilinear form as I just defined, and L is linear. So in the first statement, we don't need an inner product. We just need that A is a bilinear form and L is linear. Then let's assume U solves the continuous problem 629 in V, and UH solves the approximation, the approximate weak form 633. Then we can prove, and I'll do it in a minute, that the error U minus UH is orthogonal, is A orthogonal to any element in the approximation space VH. So any element in VH, in capital VH, if I put it into the bilinear form together with the error U minus UH, then it's the result is 0, and this is called Galerkin orthogonality. Let me just write it so that you don't have it only half here. So Galerkin orthogonality. If in addition A is an inner product, so if we also assume that A satisfies the second conditions, namely that it's symmetric and that AV comma V is greater or equal to 0, with 0 being 0 only for the trivial solution, then we have this result, which is now a very strong result. So this is called Sayer's lemma. Namely that the error that we commit, U minus UH in the energy norm, is less than or equal to any the error by any other element of VH. So there is no better element in VH to approximate U. So UH is the best approximation to U contained in VH. So this would be 642. And this would be 643. Let's prove this. It's very straightforward using the conditions. So since VH is a subspace of V, we can use the continuous setting here. So VH is a subspace of V. So this has to hold also for any element in VH. So we get that A U comma VH is equal to LVH for all VH in VH because it's a subspace of V. Now we can subtract 633 and use linearity, the linearity of A, then it follows. So we know also that AUH equals LVH. So in particular, we can subtract and we get a U minus UH VH is equal to a U VH minus a UH VH, which is L VH minus L VH, and thus 0. So in particular, we have shown Galerkin orthogonality for all VH in VH. Now, using this Galerkin orthogonality, hence, if A is also an inner product, it follows for all VH in VH again. So now we want to study the error. Let's make start a little bit further to the left here. So we want to study the error U minus UH in the A norm. Remember? We want to show this result now. Zayer's lemma. So we start with U minus UH in the A norm and we square it for simplicity. Then by definition of the energy norm, that's nothing else than A U minus UH U minus UH. Now we can add and subtract VH. So U minus VH plus VH minus UH. And use linearity to get a U minus UH U minus VH plus a U minus UH VH minus UH. But that thing here is an element of VH. And now looking above here, we've just shown that for any element VH in the subspace, oh, you can't see it anyway. So we've shown this. And so for any element in the subspace VH, this inner product AU minus UH with VH minus UH is 0. So this whole thing here is 0. Okay, now I can use Cauchy-Schwarz and I can say that AV, W in the A inner product is less than or equal to V in the A norm times W in the A norm. So in particular, we get here that a U minus UH, U minus VH is less than or equal to U minus UH in the A norm times U minus VH in the A norm. By Cauchy-Schwarz. So using the Cauchy-Schwarz inequality 641. Okay, now what have we proved? We have shown that the square of the energy norm of the error is less than or equal to the energy norm of the error times the energy norm of U minus VH for any VH. in VH. Okay, so either we have 0, either U minus UH in the A norm is 0, then the fact that UH is the best approximation holds trivially, because obviously we can't approximate better than by having a 0 error. Or if the U minus UH is not, in the A norm is not 0, we can divide. Or we can divide by U minus UH in the A norm to again obtain the result. Okay, so what have we proved? We have proved that if we have a bilinear form, then our weak form and the approximate weak form, the solutions of the weak form and the approximate weak form are, the error between them is orthogonal to the subspace in which we're solving the approximate weak form, and if the bilinear form A is in fact an inner product, we have best approximation in the A norm. Okay, let's apply this now to our example. Okay, so returning now to the specific A and L. So returning to the differential equation 627 and its weak form 629. And 630. So with the specific choice of bilinear form and right hand side. And just recalling the spaces, so we again choose our V, as I wrote at the very beginning in the revision, to be all continuous functions on 0, 1, which have bounded and piecewise linear, piecewise continuous. Derivative on 0, 1 plus boundary conditions. So V of naught is V of 1. Okay, and just to make it clear again what our bilinear form is, our bilinear form was integral 0, 1 k u prime v prime dx, and our right hand side functional was integral 0, 1 f v dx. Now it is easy to show, I've already hinted when we did the definition of inner product, it is easy to show, similarly to 631, which was the result I quoted from the proof of existence and uniqueness before, that A is in fact an inner product on that space V, but I believe it might be an exercise on the problem sheet. So, and if not, you can try out proving it yourself. Now let 633 be the approximation in the piecewise linear finite element space. VH defined in 639. I had it above. So it's basically a continuous, the space of all continuous functions that are linear on each subinterval xi minus 1 xi and satisfy the boundary conditions. Then we can use the abstract theorem. So our bilinear form satisfies the conditions. VH is a subspace of V. That's finite dimensional. In fact, that's not even needed. And we can just use C as lemma. So U minus UH, the approximation in the finite element space, has to be less than or equal to U minus VH in the energy norm for all piecewise linear functions on the mesh. So in VH. In other words, writing it in explicit form, integral 0, 1 k times u minus UH all primed squared dx, which is the energy norm, square root, is less than or equal to integral 0, 1 k u minus VH all primed squared dx for all VH in VH, and that's 644. Now the left hand side, we already said it's a norm, so the left hand side of 644 is a measure, a norm in fact, of the error u minus UH, where u of course is the unknown exact solution, and UH is the thing that we're actually computing. But we can a priori now, in an exact analysis, say how close the error is without knowing u. Okay? So this is our classic numerical analysis tasks. So we want to prove that UH converges to U as the mesh size H goes to 0. And for doing that, we need to pick, because we know that this inequality holds, so we don't need to prove it for our solution U minus UH. We just need to choose a clever VH in VH for which we can bound the error or show that it converges, and then it also holds, of course, for U minus UH because that's the best approximation. So we need to pick a clever VH in VH such that the right hand side of 644 can be estimated in terms of H, and in that way we also get an order of convergence. We don't only get that it does converge, but we also get how fast it converges as H goes to 0. And now for this, typically we go back to numeric 0 and say, what do we know about approximating functions by piecewise linear functions? Well, we can use interpolants. So for the analysis, we now assume that U is known and we build an interpolant, and then we get the error. But that doesn't mean we need to know the function or we need to know the interpolant, because we have 644. 644 says the thing we compute by solving 633, the approximate weak form, has an error that's less than any function I can choose in a piecewise linear space. So this is just for theoretical purposes now. So we make use of the piecewise linear interpolant of the exact solution u. So for any continuous function v on 0, 1, we can introduce, I call it pi h v for the interpolant, and it's simply sum I equals 1 to n. If we want to interpolate, because our basis functions phi I were chosen such that they're 1 at one vertex, remember, and 0 at all the other vertices, so we simply can define our interpolant by evaluating the function we want to interpolate at the grid points and multiplying with the basis function and add it up. With phi j, the hat functions given in section 6.4.2. So first of all, obviously it's a linear combination of it's spanned by the basis function of VH. So clearly pi h of V is in VH. And as I said, if I evaluate pi hv at a grid point xj, then we get sum I equals 1 to n vxi phi I at xj. But we know that phi I at xj is essentially 0 if I is not equal to j, and it's 1 if I is equal to j. That's how we defined it. And so essentially all terms here cancel apart from the one for the index j, for all j equals 1 up to n. So in other words, that is pi hv interpolates v at the grid points xj, j equals 1 to n. In fact, also at 0 and n plus 1 because of the boundary conditions, but we'll get back to that. Okay, now we can analyze the error. So we've already analyzed that the error in the finite element solution is less than or equal to u minus vh for all vh in vh. So now we're gonna just stick vh to be pi h of u and analyze that. And for that we need a norm. So we first of all recall the norm that I've already defined in numeric 0, and maybe we've used it also already in numeric 1, I can't remember. But for any continuous function v in C01, the uniform or infinity norm is simply taking the maximum of the moduli of the v of x. So basically the maximum absolute value of the function at any point on the interval. And then I can say prove the following result for our interpolation. Suppose u solves 629, and suppose u has two continuous derivatives on 0, 1. Then the interpolation error u minus pi hu, the derivative of that in infinity norm can be bounded by h times the infinity norm of the second derivative of the solution u. So before we prove this lemma, so this will be the last thing of this section, before we prove the lemma, Let's note the consequence. So now let us write down our final convergence result. This is the main theorem of this section, finite element section. If you solve 629, the weak form, and you solve 633 with, I should maybe say with piecewise linear finite elements, with VH defined in 639. Then U minus UH in the energy norm is less than or equal to H times the infinity norm of the coefficient K, square root of that, times the infinity norm of the second derivative of U. So as H goes to 0, we see that the error goes to 0, because these two things are assumed to be bounded. Okay, so let's first prove this consequence. So we're going to use the result in lemma 64.8 up here in order to prove this. So squaring 644, that's the Sayers lemma, the best approximation, and choosing VH to be pi HU. I've already given you the plan before. It now follows from this lemma that I've just stated that. Okay, so we're going to use this result here and the Zea lemma, so that U minus UH in A norm is always less than or equal to U minus VH for any function in the subspace. So U minus UH in the A norm squared is less than or equal to integral 0, 1 K U minus pi HU primed squared dx to the half. So that's just substituting VH to be pi HU. Now, we know that K is continuous and even continuously differentiable, so we can take the maximum of K out. So there's no square root here, sorry, because I've squared it. So we can take the maximum of K out of this. Why do I need this? I don't need this anymore. Okay. So this is less than or equal to the maximum of K times what's left here is the square of the first derivative of U minus pi HU, so I can pull that out as well. So I can take that, because U is 2 times continuously differentiable, so U minus pi HU primed in infinity norm squared. And then all that's left is the integral from 0, 1 dx, the length of the integral at the interval, and obviously that's just 1. So in total, using the result from lemma 6.4.8, this is less than or equal to h squared times k in the infinity norm times u double primed in the infinity norm. Just recall, the derivative of u minus pi hu in the infinity norm is less than or equal to h times the second derivative of u in the infinity norm. And so we're using this result here, and we get the result we wanted to prove by taking the square root. Okay. So before proving now this lemma that I need, so before proving essentially how to do this step, I make a remark. So remark 6.4.10. So essentially what theorem 6.4.9 shows that if u has two continuous derivatives, and all these assumptions can be made weaker, but I'm only giving you the ideas here. So it doesn't have to be continuous, it can be piecewise continuous derivatives. But if u has two continuous derivatives, then UH converges to U as H goes to 0. And in fact, it follows immediately from our rewriting by rearranging 628. So that was have a look back. I'll just do a little bit a little aside. So it was minus k u double primed minus k primed u primed equals f. So if I rearrange that, then that's equivalent to u double primed is equal to u double primed is equal to minus k primed over k u primed minus f over k. And since k was less than or equal to was strictly positive, and k primed and f were continuous, we know that u prime double prime is in fact continuous. That u double prime is continuous under the assumptions made on the data k and f at the start of section 6.4. And what have we seen? We've seen that in the norm, in the energy norm, so in the norm induced by A, the convergence is linear. I'm not going to prove it, but I'm just going to state that in fact in the infinity norm, it can in fact be shown that the u minus UH in the infinity norm is in fact order h squared. So like the finite difference method, the method of finite elements for this differential equation converges quadratically with the mesh size. And I've already said, note that the interpolant pi HU was used for theoretical purposes only. So we're not needing for this finite element method to know U or to know the interpolant of U, because in general we don't know U, of course. Otherwise, we're not gonna try to compute it. Okay, so that's the consequences of the approximation lemma here. So the consequences of this approximation lemma are that we have linear convergence in the A norm, and in fact, as I say, it can even be proven that we have quadratic convergence in the infinity norm. So let's finish the theory part by proving this interpolation result. So what am I trying to prove? So I have my function u here. So u would be the solid line, and I have my linear interpolant pi hu, which interpolates at the grid points. So here we have xi minus 1 xi, and at x naught and at xn plus 1 we have 0. In order to prove the error in infinity norm in the derivatives between those two, let's define for notational simplicity dh to be the interpolation error. So u minus pi h u. Should this really be small pi? No, this should be big pi. Okay. So let dh be u minus pi h u, and let, as we did for the time discretization methods, I believe, we called it a bit differently. We call it I'm calling the interval from xi minus 1 to xi tau I. And now we apply the mean value theorem. If you don't remember that, please look back at your analysis lectures or at numeric 0. So in numeric 0, I have given the mean value theorem and the theorem by Rolle we used several times to prove things on interpolation results. So in fact, we could probably simply quote the result from numeric 0, where we did all the interpolation theory. But I'm gonna do it one more time. So so there exists a point in the interval xi minus 1 xi, so in the interval tau I, such that by mean value theorem, dh primed at xi I, so the derivative at xi I of this function, is in fact equal to the mean value of the endpoints at the endpoints, so is equal to dh of xi minus dh of xi minus 1 divided by xi minus xi minus 1. Now we have defined pi hu to be the interpolant, so we know that at the endpoints of all these intervals, the error between the interpolation error is 0. Okay, so in total we get that dh primed at that specific point xi I is 0. So there exists a point in the interval that is where the derivative is 0. And hence, for an arbitrary x in the interval tau I except the point xi I, using mean value theorem again, it follows that there exists an eta I between x and xi I, so this could be in the interval xi x or x xi, depending on which one is to the left and which one's to the right, such that dh primed at x minus dh primed at xi. So I'm using the mean value theorem now for dh primed, divided by x minus xi is equal to the second derivative of dh at this specific point eta I. Let me just rewrite this a bit smaller so that it fits here. Okay, so dh primed at x minus dh primed at xi divided by x minus xi is equal to dh double primed at some specific point eta I between xi and x, or between x and xi. But dh is a difference between u and a linear function. And if I take two derivatives of a linear function, so we know that pi h u double primed obviously has to be 0 because it's a linear function. And so we can basically deduce that dh double primed of eta I is in fact simply u double primed at eta I. Since pi h u is linear on tau I, and thus pi h u double primed of eta I has to be equal to 0. So what have we shown? If we rearrange this, that for any point x in tau I, so let's write it as a mathematical statement. For any x in tau I, there exists a xi I and an eta I in the interval tau I such that dh primed of x, so this is 0 again, remember? We've just proved that above. So dh primed of x is equal to x minus xi times u double primed at eta I. And now I don't have to exclude, so before we excluded, here we excluded xi, but here I don't have to exclude xi anymore because the result is true anyway when x is equal to xi. Then I've just got this result here. Okay, so this result holds for all x in tau I. And in particular, this implies, now using some upper bounds, some norms, that so dh primed is exactly what we wanted to bound, because dh primed is u minus pi h u, so we wanted to bound exactly here u minus pi h u primed. So this is dh, remember? So this is dh primed. So the infinity norm of dh primed is what we want to bound from above. So now we know that for every x, dh primed of x can be written like this. And so in particular, we can take the maximum. So we can prove that u minus pi h u primed in infinity norm, which is defined to be the maximum over all x in tau I. Oh, yeah, that's why I did it this way, sorry. So first we take the maximum only over each element. So for an element tau I, we know now that the maximum of u minus pi h u primed in modulus of x in modulus is equal to the maximum over x in tau I modulus x minus psi I times modulus u double primed of eta I. So we can obviously bracket this because the u double primed of eta I doesn't depend on x. And so this thing is less than or equal to the mesh size because both points are in the interval tau I. And so we have in total proved that the maximum of this first derivative of the error, interpolation error, is less than or equal to h times the maximum of x in tau I of the second derivative of u on that interval. And then finally we just need to take the maximum over all tau I. So taking the maximum over I equals 1 to n leads to the result. Let me just show you. So max I equals 1 to n of max x in tau I of u minus pi h u primed of x is of course nothing else than max x over the whole interval 0, 1. If we take the max over all intervals and the points in each interval, then that's the same as taking the max over the whole interval. And that was our definition of the infinity norm. Okay, so we can do that on the left, we can do that on the right, and we get our result. Okay, so what have we proved? We have proved our interpolation result here in lemma 6.48, and before that I'd already proved how this implies linear convergence in the A norm of our finite element solution. So let me give you a couple of final comments on this section on the finite element method. So in essence, this now completes the basic description of the method and of the analysis of piecewise linear finite elements in 1 dimensions. So this can now be extended very easily, and it's a real DIY. I can put a DIY here because it's really straightforward to extend this to higher order. So I said before that the analysis for higher order in the finite difference method is a little bit involved. Here, all you do is simply exchange the space VH of piecewise linear functions in 639 by a space of piecewise quadratics, piecewise cubics, piecewise polynomial functions of higher order. And then all you need to do is redo lemma 6.4.8. In fact, look back at numeric 0, where we've proved interpolation results for piecewise quadratics, piecewise cubics, etc., and where we've shown that provided, so exactly this result here, in numeric 0, we've shown that if pi h, for example, was the kth order polynomial interpolant, then essentially all you need to do is you get k here and you get k plus 1 here. So the k plus first derivative. Okay, so you can easily check that yourself, that this works. So the analysis carries over very straightforwardly to higher order, and the basis functions, I haven't written this down. The basis functions in the quadratic case, let me give you the quadratic case. So in the quadratic case, in the linear case, on each element tau I, we had basis functions essentially like this. So this was the hat function to the left and the hat function to the right. So these two were our linear basis functions. In the quadratic case, all you do is you add another degree of freedom at the center, and you add, for example, a quadratic bubble. So this function, it has support only on the interval tau I, and you have a quadratic function on that interval, and then the basis, that gives you the basis for the quadratic. So you have functions here, here, and here. So that would be the hierarchical basis. There is a basis of 3 quadratic functions as well. But in essence, what you see is that the finite element method is, as I said right at the beginning in my first video, is kind of the equivalent of the Runge-Kutta method for finite for boundary value problems in ODEs, because instead of taking more and more points into account further out in the high order finite difference methods, the high order finite element methods just add points inside the interval. And what's even more important, and really the reason why also here in Heidelberg we continue mainly with finite element method in the higher semesters, is because it is much easier to extend to higher dimensions and to partial differential equations. So there's a whole course, numeric 2, which is taught by Peter Bastian next semester, and I highly recommend for those who have been excited or interested about this subject to go to this course, because it's really powerful stuff and can be used for many applications. Okay, so in the final part of this section, I will now describe a little bit more about how to solve the arising linear boundary value problems. I've already said in the when I wrote down the finite element system that we can use the Thomas algorithm, Gaussian elimination of tridiagonal matrices, and efficiently solve solutions of these finite element and finite difference methods. However, in general, and especially when you have higher order finite elements, finite differences, this is not possible, not so easy. And so really what people use, and especially also in higher dimensions for partial differential equations, is iterative methods. So let me finish now this section by telling you a bit about iterative methods for discretized linear boundary value problems. So initial value problems, we're stepping forward in time. We can just solve interval by interval, one at a time. Boundary value problems, the difference right at the beginning, I said, was that you cannot do that because you have conditions specified at both ends. You need to solve all values together. So you get to a problem of linear algebra. So as we've just seen, the discretization of boundary value problems with finite differences, or with finite difference, or finite element methods, leads to of linear boundary value problems, of these linear second order boundary value problems, leads to a sparse linear equation system to be solved for some vector of coefficients or of grid point values in the finite difference methods in Rn, such that Ay is equal to right hand side B. So I'll call that 645 for this section now. So let us, to finish this section now, let us discuss how to solve iteratively such a system. And we will use, on the one hand, the gradient method defined in definition 4.2.3 for general nonlinear problems. Here we are going to apply it to this linear problem, as well as, and this is the main reason of this section, to introduce and analyze the significantly more efficient conjugate gradient method. So it's also a descent method as we defined in section 4, but it's specifically tuned. I mean, there's a nonlinear version of it as well, but we're gonna look at it how it's especially efficient for linear equation systems. And also this has already been introduced at the very end, but never analyzed in numeric 0. In fact, in the same section 6.5. Okay, so restrict now. We've seen that for general second order boundary value problems, you get these triangle systems, and they are in general non-symmetric, but we restrict ourselves to symmetric positive definite, SPD matrices A in Rn cross n. In other words, the matrix is symmetric, so A is A transposed, and if I take the Euclidean inner product of AY with Y, then that is strictly bigger than 0 for all Y in Rn except 0. So that's symmetric, this is the symmetry, and this is positive definiteness. Again, from numeric 0, recall, or from your other basic numeric courses that you've done, that for such an SPT system, all eigenvalues lambda I in the spectrum of A are of such an SPD matrix A are real and positive. So 0 is strictly less than lambda 1. I'm going to number them. I order them by size. Lambda 1 is less than or equal to lambda 2, less than or equal to all the way up to lambda n, which is finite. So we will need this a lot in our analyses below. And also, like in the bilinear form we had before, the matrix A defines a norm, and when A is in fact the stiffness matrix from our elliptic problem, from our boundary value problem, it is in fact related, these two norms. And this is also called sometimes the energy norm. So this defines a norm on Rn. Okay, so now we consider to apply the gradient method, we need to minimize some functional. So we consider the quadratic functional f of y is a half Euclidean inner product of ay with y minus b inner product y for all y in Rn. In fact, I want to actually define this with x's. So f of x is a half Euclidean inner product ax with x plus a minus bx for all x in Rn, and that's 647. Okay, so now for this functional, we have the nice property that the vector y is unique solution of our linear equation system 645. So this is the linear equation system. If and only if it's also minimizer of unique minimizer of 647. So the unique solution of 645 with SPT system matrix A, if and only if f of y is strictly less than f of x for all x not equal to y. So this is a fairly straightforward result. So let's prove it. It should be fine. Okay, let's first start this way. Assume that y solves the linear equation. So let y be in Rn such that ay equals b. Now since a is SPD, it follows for any x not equal to y that f of x minus f of y, so we want to show that that's strictly bigger than 0 to prove that it's a strict minimizer, that fy is a strict minimizer. So let's write that out. So we get a half a x plus b minus bx. Okay, maybe I want to move everything over a little bit. Okay, so then it follows for all x not equals to y that fx minus fy is a half axx minus bx minus ayy plus by. Now we use that the y is a solution, and so we can essentially say that this thing here is equal to b, and so we essentially end up with, oh, the other way around, sorry. We don't want to make this equal to b. We want to make the b's equal to a's. So we use that this is equal to ay, and this is equal to ay, and then put it all together, and we get that this is equal to a half ax comma x. So we get twice the 2's are missing somehow. Ah, yeah. Sorry, the 2's are missing. Because I've pulled the half out. So minus 2 times and plus 2 times. Okay, so now I put it back together, so I get axx from here. I have minus 2ayx from here. And I have these two I can pull together, and I get plus a yy. Now that's just, I can pull this all together by linearity, and this is simply a half inner product a of x minus y with x minus y. And because this is a SPD matrix, we know that if x is not equal to y, then this is strictly bigger than 0. That comes from SPDness. Okay, so we have proved that if y solves a y equals b, then it minimizes f, is the unique minimizer of f. So now let's look at the other direction. So conversely, if f of y is strictly less than f of x for all x not equal to y, then it follows necessarily that the gradient of f, so the first order optimality condition, gradient of f at y is equal to 0. So let's look at what the gradient of f is. So let's look at df by dxi of x, and I'll do it just very elementary. I write out everything in sums, so I get a half sum j k equals 1 to n x j a j k x k. That's the inner product of ax with x, minus, and the inner product of b with x is simply sum j equals 1 to n bj xj. Now taking the derivative of that is simply, I get 2 times, this is a quadratic, each of them is a quadratic, only when the two terms are, one of the terms is non, is equal to xi, do I get a result, so I get a single sum out. aij xj minus bi. So here only when I have xi do I get a contribution, and it's bi, and here I get two contributions, once when this is xi, once when that is xi, so the half cancels, and because of symmetry it doesn't matter whether it's the left or the right of them. and this is true for all I equals 1 to n. So what have we proved? We have proved that df by dxi is simply the ith row of the linear equation system. So this implies, because we have that the gradient of f has to be equal to 0, this implies ay equals b. Okay, so we can find solutions to our system ay equals b by minimizing this functional over all x in Rn. Okay, we've already done this, and we've already defined a method to do this, namely the gradient method. So we did it for general nonlinear functionals, but here now we have a quadratic functional. And so we want to exploit all the properties of this quadratic functional. In particular, we can do a lot of things explicitly. So if you don't remember the gradient method, please halt the video and have a look back at section 4. In particular, we defined the descent methods there, and then a special descent method which where we used the negative gradient as the search direction or the descent direction. And we apply this now to the quadratic functional in 647. So that is our descent direction a descent method, sorry. We're applying a descent method with descent direction or search direction s in the kth step is simply minus gradient of f at the kth iterate xk, and for simplicity in the following, I'll define the gradient by at the point xk by gk, so g for gradient. And the other ingredient in our gradient method, in our steepest descent method, was a line search. And in particular, we can now explicitly solve this line search. We don't need to do step size control. We can explicitly solve the line search, and that's what I'm going to do in the next bit. So that's the definition, the theoretical definition in definition 4.23. Alpha k was chosen to be the minimum over all positive gammas, or the argmin over all positive gammas of f minimized in the search direction. So xk minus gamma g of k in the kth iteration. So in the kth iteration, we choose that particular search direction and that particular alpha. Okay, now let's work out what gk and alpha k are, because we can explicitly work them out. Yeah, I have enough space here. So note that since gradient of f of xk, or gradient of f of x, we've just shown in the last proof that the gradient is in fact ax minus b. So let's look back here. We've seen that the gradient or the derivatives of f in the direction xi is the ith row of the of ax minus b. And so we're going to exploit that now. So we can work out the gradient at the next iteration, so grad f of xk plus 1 is equal to, let's put it in, is a times xk minus alpha k gk minus b. Just substituting. The k is first iterate in the gradient method, in the steepest descent method. But axk minus b, this bit here, is just gk. And so in total, this is equal to gk minus alpha k agk. And so that's how to compute the gradients. So instead of actually evaluating f, we just have to take our previous gradient and subtract alpha k a gk from it. And to get the alpha and the minimum, the line search parameter alpha k of the function f of xk minus gamma g of k in the kth iteration sorry, I've jumped the line. And the minimum alpha k of this function is attained when gamma satisfies so we need to minimize here this function. So again, we need to minimize this function. So we use again a minimum of this function has to have first derivative equals 0. So we have to have 0 is d by d gamma of f of xk minus alpha k gk, sorry, minus gamma gk, which, substituting in or using the definition of the chain rule, is minus Euclidean linear product of grad f evaluated at xk minus gamma gk with inner derivative gk. And now using the definition of the gradient, or we know what the gradient is, namely here, we get b minus a xk minus gamma gk with gk, which we can by linearity separate into, so I can take those two together here, and that's obviously gk again. So these two are just gk, and so essentially I get gk with gk, and plus, because there's a minus and a minus, plus gamma times a gk with gk. And if I rearrange this, this leads to the following iteration. For finding the solution y in Rn of a y equals b. So maybe I'll just give this this last condition already here because we did the result. So if I rearrange this, this simply tells me that gamma should be, or that alpha k should be, the minimum should be minus gk divided by a gk. Where's the minus gone? Minus mistake somewhere. I'll double check for the minus. I will not find that quickly now. So this condition, so now we have a special form of grad. So grad f is gk minus alpha a gk, and alpha k is up to this sign, which seems to be wrong in my derivation here, equal to the inner product of the gradient with itself, and then alpha a times the gradient with gk. So the gradient method now, with these specific choices of alpha and the search direction, can be written given an initial value x naught in Rn. Let's define the initial gradient g naught. We need to compute that to be ax naught minus b. And then to compute the next iterate, we compute this alpha k. I'll double check the sign. We can compute the update by computing xk plus 1 as xk minus alpha k gk, and we can update the gradient for the next iteration to be gk minus alpha k a gk. And this whole method we'll call the gradient method for linear systems, or for this quadratic functional we call 649. So now suppose A is SPD, then we have the following theorem. The gradient method in definition 652, just given, converges for any x starting vector x naught in Rn to the solution of 645, the system linear equation system, and the error in the A norm satisfies the following bound. So the error at the kth iteration in the A norm, recall the A norm was simply ax with x square root of that. The largest eigenvalue lambda n of A minus the smallest eigenvalue lambda 1 divided by the sum of the two to the power k times the initial error x naught minus y. So this is the convergence rate. So the convergence rate is determined or is bounded by this ratio of differences and sums of the eigenvalues of A. Okay, so I have done 5 minutes less last time. So strictly speaking, we have another 5 minutes, but I think I'm gonna give you those, and I will give the proof in the next video. So the proof now, I'm gonna prove now that this is true, that this gradient method does converge, and that we have this rate. But one thing I want to observe already straight away is that if lambda n is much bigger than lambda 1, and we will see that in an example later. So if the largest eigenvalue of the matrix A is much larger than the smallest eigenvalue, remember they're all bigger than 0, then this rate which is lambda n minus lambda 1 divided by lambda n plus lambda 1 is very close to 1. Okay, so if I subtract a very small number from lambda n and add a very small number to lambda n, then the numerator and denominator will be very close, and so the convergence rate will be very poor. In fact, we will see that for the finite difference method, even for, so we will see that for finite differences and finite elements, lambda n minus lambda 1 over lambda n plus lambda 1 is about 1 plus some constant. Let me see what the constant was. Is 1 minus pi squared over 2 h squared plus order h to the fourth. So we will see that even for h equals 1 over 40, we already get that this thing is 0.997 or something like that. And so if you're reducing the error in each iteration just by a factor 0.997, you will need a long time before you get the error to be below some tolerance. Okay, so the convergence rate of this gradient method is fairly poor, which will then lead us to discuss the conjugate gradient method. Okay, I'll finish here, and I will have one and a half more videos on this iterative solution of the discretized systems next week. Thanks.